And now we're live. Okay. Precipitation reactions. The net ionic equation. So, we present precipitation reactions in a couple of different ways. Please don't bump the microphone, pup. First, we have the molecular equation. This is what we've already seen, where it presents all the compounds as if they were molecules. Okay. Now, they're ionic compounds, so we know they don't have molecules. And on top of that, these things are in solution, and we know that when a salt dissolves, it dissociates into ions. So here we have potassium sulfate and calcium nitrate, making potassium nitrate and calcium sulfate. They swap their partners. So this is a convenient way of writing this because it's all got all the information right there in one place. But we know that that's not how these things actually are. These guys are split up into potassium and sulfate, and these two are split up into calcium and nitrate, and these two are split up into potassium and nitrate. Now, the calcium sulfate is a solid. It's insoluble, so it doesn't dissolve in water, so it's not dissociated. So what we do is from there we have our ionic equation, where we take all of our aqueous compounds and break them apart into their component ions. So here we have our potassium sulfate. The potassium, there's two of those, so we get 2 of K+. Here we have sulfate, so that goes to SO4 2-. Here we have calcium, all by itself, calcium 2+. And NO3 1-. The nitrate, there's 2 of those, so we get 2 NO3 1-. And then likewise, the potassium nitrate is floating around in solution. It's all dissociated, so we get 2 of the potassium and 2 of the nitrate. And then, like I said, the calcium sulfate is still together. It's not dissolved, so it's not dissociated. Now, like I said in the previous thing, you're going to need to do a little bit of practice with this. You need to get good at recognizing your monatomic ions and your polyatomic ions and knowing when the subscript comes up in front and becomes a coefficient. Over here, we have a different situation. It's not that a subscript has become a coefficient. It's that we have the coefficient, which means there's 2 potassium, so 2 potassium right there, 2 nitrates, so there's 2 nitrates down there. All right. Now, the thing is, not all of those ions are actually doing anything. Okay. So here we have 2 potassium floating around in solution, and over here we have 2 potassium floating around in solution. Here we have 2 nitrate, and over here on the product side we have 2 nitrate. The potassium and the nitrate remain in solution. They're not actually participating in the reaction. They're just watching the reaction. So we call them spectator ions. And all that's really happening is that the calcium and sulfate ions that are floating around in solution, they run into each other and bloop, they fall out of solution as a precipitate. So that's the only thing that's actually changing. Anything that remains the same on either side of the arrow, we cross it out, we get rid of it. And what we're left with is the stuff that's actually participating, the calcium and the sulfate. Okay. So it almost doesn't matter what the calcium and the sulfate are partnered with. So long as they're free floating in solution, when calcium runs into sulfate, it'll precipitate. The calcium could have been paired with chloride or something like that. The sulfate could have been paired with sodium. Okay, and you would get the exact same result: sulfate and calcium coming together to make calcium sulfate. So, why don't you go ahead and do a bit of practice? Take each of these reactions, break apart your aqueous compounds, and make your ionic equation. Then identify your spectators and write the net ionic equation. You're going to need plenty of paper for this, but I have confidence in you. You can do it. So go ahead, pause it, do these 4 things, and welcome back. Okay, so now I'm going to go through and I'm going to do the boring work for all 4 of these equations. So we have HCl, aqueous, and sodium hydroxide, aqueous, reacting to form sodium chloride, aqueous, plus H2O, a liquid. All right, so I'm kind of cheating here. This is actually an acid-base neutralization, but it follows the exact same rules as precipitation. So H plus Cl minus plus Na plus OH minus. I should be writing aqueous under all of these, but that would take forever, and you wouldn't be able to read it anyway. So Na plus Cl minus plus H2O. It's a liquid. All right. So this is our ionic equation for this particular reaction. So now we just go through and we identify our spectator ions. We have sodium and chloride. So those guys are spectators. They just watch. We're going to get rid of them. And that is how we'll get our net ionic equation. H plus OH minus coming together to make H2O. Next up, we have our old friend potassium iodide and lead 2 nitrate. So 2 potassium iodide plus lead 2 nitrate, aqueous, makes 2 potassium nitrate, aqueous, plus lead 2 iodide, solid. It's a very pretty yellow salt. All right, so now we are once again going to break everything up. We have 2 potassium ions here, so 2K plus. We have 2 iodides, so 2I minus. We have 1 lead, so Pb2 plus. We have 2 of our nitrates. See, this is subscript. So 2 NO3 minus. Then 2 of our potassium, 2 of our nitrates. And the lead 2 iodide is solid. It doesn't break apart. Okay. So once again, we identify our spectators. Potassium is the same on either side. Nitrate is the same on either side. They don't change. They don't actually participate. We don't care about them. So what we're left with is lead 2 plus 2I minus coming together to make lead 2 iodide solid. All right. Fresh page. Next up, we have sodium fluoride plus calcium chlorate. Okay, you're going to be getting a lot more practice with these salts. All right, so 2 sodium fluoride plus 1 calcium chlorate. Oops. Goes to form 2 sodium chlorate and calcium fluoride. Herbie Katie. So calcium fluoride, sodium chloride. All right. So once again, we break it up into component ions. 2 sodium 1 plus, 2 fluoride 1 minus, 1 of our calcium 2 plus, 2 of our chlorate 1 minus, going to form 2 sodium 1 plus, 2 chlorate, ClO3 1 minus, and finally CaF2 solid. All right, so once again, we see sodium hasn't changed, chlorate hasn't changed. Those are spectators, so we go ahead and we get rid of them. And what we're going to be left with is just our fluoride reacting with our calcium to make calcium fluoride. So these things are a little tedious, but not too hard. Just a little bit of practice and you'll be okay. And now finally, magnesium reacting with hydrochloric acid. This one is also a little bit different. This is actually a redox reaction. You might remember that as one of the examples I gave. Okay. So now we have our magnesium, we have our hydrochloric acid, we have magnesium chloride and hydrogen gas. Let's do the thing. Get our ionic equation. So magnesium isn't even an ion over here. It's just solid magnesium. But the HCl does ionize 100%. So we have 2H plus and 2Cl minus. Now we come over to the right. Magnesium has reacted. It's lost electrons. So now it is magnesium 2 plus. Our chlorine hasn't changed. It's still just chlorine 1 minus. And then our hydrogen gas, it's a gas. So it doesn't break up into anything either. Which means that for this one, there's only one spectator. It's just the chloride. Okay? Magnesium has changed to magnesium 2 plus. Okay? It's no longer the solid metal. It is now an ion. Likewise, hydrogen has gained electrons. It's gone from being the ionic acid proton, and it is now hydrogen gas. So chloride is the only spectator ion. Meaning our net ionic equation is magnesium metal plus 2H plus. React to form the magnesium ion and hydrogen gas. All right. So those are net ionic equations. I have no idea how they'll ask you to do these on the new Blackboard tests, but they'll be on there somehow. They'll ask you to do it in somehow, some way, because they kind of have to. All right. So those are net ionic equation. That's how you do them. And with that, we have finished another set of slides, and I will see you in a few minutes for the next lecture when we start talking about how we predict solubility. How are we going to recognize insoluble salts? That's going to be the